Hi, welcome to my channel Smart Easy. Today I'll explain one complete problem which describes the design of low pass Butterworth digital IAR filter. Let us see the problem. Design a low pass Butterworth digital filter to give a response of 3 dB or less for frequencies up to 2 kHz and an attenuation of 20 dB or more beyond 4 kHz. Use the bilinear transformation technique and obtain H of Z of the desired filter. So before we start our actual problem, let me explain one important concept, that is, this is the another popular unit that is used for filter specifications is dB. Generally, the filter specifications has to be mentioned either in terms of the gain. Another method is has to be expressed in terms of a dB. In this particular problem, the total data is given in terms of a dB. So when the gain is expressed in dB, so it will be a negative dB. Otherwise, when the attenuation is expressed in dB, it will be a positive dB. So let K1 is a gain in dB at a passband frequency omega 1. Assume this. And K2 is a gain in dB at a stopband frequency omega 2. So if K1 and K2, these two are gains expressed in dB. So we have to get the normalized values of the gain or the normal values of the gain in terms of A1, A2 with the help of the following formulae. See here, 20 log A1 equal to K1. This is the relation to convert the gain K1 in terms of in dB to the normal gain in terms of A1. So 20 log A1 which is equal to K1. So from this we can derive that A1 is equivalent to 10 power K1 by 20. Similarly, 20 log A2 equal to K2, log A2 equal to K2 by 20. So similarly, A2 equal to 10 power K2 divided by 20. So using these concepts, we have to start this problem as per the procedural steps already we learned in the previous video. First, understand the given data. Here, attenuation at a passband frequency is 3 dB. So the gain has to express with negative sign, that is K1 gain at a passband frequency omega 1 is a minus 3 dB. Therefore, we can get the normal value of A1 which is equal to 10 power K1 by 20. So 10 power minus 3 by 20 which is equivalent to 1 by root 2. Similarly, the attenuation at a stopband frequency omega 2 is 20 dB. So the given gain K2 at a passband frequency omega 2 which is expressed with a negative sign as minus 20 dB. Here you try to understand clearly when the gain or attenuation is expressed in dB, definitely you should have a positive sign convention, right? So for gain has to be expressed in dB, it could be a negative sign convention. So from that we can get the normalized value of gain A2 which is equal to 10 power K2 by 20, 10 power minus 20 by 20 which is equal to 0.1. And also the given data passband edge frequency is given as 2 kHz and stopband edge frequency is given as 4 kHz. To continue our problem, let us assume the sampling frequency here we have to assume which is nothing but 10 kHz. Why should we get the sampling frequency is? First of all, we have to get the normalized values of the frequencies in terms of the radians per second. Actually, the frequency mentioned in the given problem is in terms of the hertz. In order to convert the hertz frequency in terms of the radians per second, we have to use the following relations. So, for example, if you want to have a normalized frequency omega 1, which is equivalent to 2 pi f1 by fs, which is equal to 2 pi into, we know that f1 equal to 2 kilohertz, that means 2000 divided by 10,000, which is equal to 0.4 pi radians per second. Similarly, omega 2, 2 pi f2 by fs, 2 pi into 4000 divided by 10,000, which is equal to 0.8 pi radians per second. After getting this all basic information, let us start the designing procedure of Butterworth digital IAR low pass filter. We have to follow the step-by-step procedure. The first step, as all of you know, we have to follow is we have to choose the type of transformation that we are going to be using in our problem. Here I told you already, bilinear transformation is chosen. Step 2, ratio of analog edge frequencies omega 2 by omega 1. So as all of you know, the formula for omega 1 is 2 by t tan omega 1 by 2, which is equal to 2 by t tan 0.4 pi by 2. Let us assume t equal to 1 second, so that you will be getting 1.45308 radians per second. As all of you know, this is the normalized values. If you want to have an unnormalized value, let us multiply the above value with 10,000. So you will be getting 14,530.8 radians per second. Another frequency, stop band frequency, that is omega 2 is 2 by t tan omega 2 by 2. Substitute all the values, you will be getting 6.155219 radians per second. Again, this is a normalized value. If you want to have an unnormalized value, multiply the above value with 10,000, so that it will be 61,552.19. Let us take the ratio of omega 2 by omega 1, which you will get 4.236. Step number 3, find the order of the filter n. Using the above relation, n is greater than or equal to 1 by 2 log of 1 by a2 square minus 1 divided by 1 by a1 square minus 1, the whole divided by log of omega 2 by omega 1. Substitute all the values. Here you will be getting n is greater than or equal to 1.59. As all of you know, as per the procedure, we have to choose the value of n such that it should be a greater or equal to the value we obtained. So here we obtained the value is a 1.59. So that we have to choose the nearest higher value or equal to 1.59 is approximately a 2. So that let us choose the order of the filter n equal to 2, which is an even number. Step number 4, analog cutoff frequency omega c. Using this formula, omega 1 by a1 square minus 1 whole power 1 by 2n. Substitute all the values, you will be getting 1.4530. As all you know, this is a normalized cutoff frequency. In order to get unnormalized omega c, as usual, multiply to 10,000, you will be getting 14,530 radians per second. Step number 5, transfer function HA of S. HA of S is nothing but analog filter transfer function that we have to get using this formula. For n equal to 2, HA of S is omega c square divided by s square plus b1 omega c s plus omega c square, where the constant or the coefficient b1, which is equal to 2 sine 2t minus 1 into pi by 2 into 2, so which is equal to 1.414. After substituting all the values, HA of S, the analog filter transfer function, which is nothing but 15,530 whole square divided by s square plus 1.414 into 14,530 into s plus 14,530 whole square. So this is the transfer function of an analog filter. Now step number 6, Here we have to convert the analog transfer function HA of S into a digital transfer function H of Z of a filter using bilinear transformation. As all of you know, in bilinear transformation we transform HA of S by substituting S equal to 2 by T into 1 minus Z power minus 1 by 1 plus Z power minus 1 for getting digital transfer function H of Z. So substitute H of Z equal to 14,530 whole square and simply substitute wherever S is there. In place of a S, substitute 2000 into 1 minus Z power minus 1 by 1 plus Z power minus 1. Simplify this above equation. Finally, you will be having in this form H of Z equal to 0.528 divided by 2.5552 minus 0.946 Z power minus 1 plus 0.5008 into Z power minus 1, which is the desired digital filter transfer function. After getting this, by selecting proper structure, we have to realize this kind of a digital filters. Thank you for watching. For more updates, please subscribe my channel. Thank you.